Okay, so we're now going to be looking at atmospheric pressure. So let's look at this question. It says, sketch a graph showing how the atmospheric pressure changes with height above the Earth's surface. Okay, so essentially as we go up, okay, as we increase our height from the Earth's surface, essentially the gravitational pull of the Earth is obviously going to decrease, which means the average weight of our gas molecules or particles is actually going to decrease. So they're going to weigh less. Okay, so that means less force. Also, the higher up we go into the atmosphere, it actually gets colder, and the particles actually get spread out even more, which means we're going to have less collisions between them, and essentially we're going to have a lower pressure. So you need to be able to describe why pressure decreases as we go further up into space. Okay, so it's summarized here. Right. Also, you need to know that the pressure in a fluid is due to the actual arrangement of the particles, so the amount of kinetic energy that the particles have, but also the atmospheric pressure pushing against it or on top of it. Okay, so if we've got some seawater, okay, yes, it will exert some upthrust upwards, okay, so we've got an upward pressure force, but we've also got the atmosphere pushing down on it. Okay, and just another weird thought for you to think about on our planet, our atmosphere actually keeps our eyeballs inside their sockets, you know, and if we went into space where there is no atmosphere, obviously you would die of no oxygen if you took off your helmet, but your eyes would actually go away from your sockets because there would be no pressure in space. So yeah, so that's one thought for you to think about. Okay, so atmospheric pressure on Earth is actually quite useful for us. Also, you should know that the pressure in a fluid causes a force at 90 degrees to any surface. Okay, so just bear that in mind. Again, so as promised, this is the pressure equation. So pressure is equal to force divided by area. Okay, so units of pressure are pascals or newtons per meters cubed, but essentially it's the ratio of the force over a specific surface area. Okay, so if force increases, pressure increases. If force decreases, pressure decreases. If area increases, pressure decreases, and if area decreases, pressure increases. Okay, so pause the video, just so numerically put some values into force and area, and then check just to verify that what I've said is correct. Okay, it's just simple maths. Right, now let's have a look at this this graph here. So it says the pressure in a liquid depends on the depth below the surface and the density of the liquid. Sketch a graph showing how the pressure in a liquid changes with increasing depth and label it A. And then sketch a second line for a liquid with a higher density. So here we go. This is the line here drawn here, and then we need to draw another line with a liquid with a higher density. So it should have a higher gradient, so that means for a lower depth we should have a higher pressure. Okay, so that because simply it's more dense. Okay, which means the particles are obviously going to be pushing against each other a lot more harder than the other liquid. Okay, liquid A. So as depth increases, pressure increases, and as density increases, pressure also increases. So it says explain why depth affects pressure in this way. Well, as depth increases, there is more of the liquid above it pushing downwards, which means, as we know, pressure is equal to force divided by area, and the force, which is the weight, will literally be bigger. Okay? Explain why density affects pressure in this way. Well, a higher density means more mass in the same volume. More mass means more weight, so that the force increases. This makes the pressure bigger. Okay, so let's put those concepts together. They can be summarized in this equation here, which you don't need to know, but you need to know how to use, okay, as always. So, the pressure, okay, of the liquid will equal to the height, okay, from the surface, okay, multiplied by the density of that liquid times the gravitational field strength, okay, which is obviously going to be 10 on Earth, okay. So, to calculate the pressure difference between the top and bottom of an object underwater, we need to calculate the pressure on the top surface minus the pressure on the bottom surface, okay? And obviously we need to work out the height as well between both surfaces. We need to know the density of that liquid, and then the gravitational field strength, and then we should be able to work out the pressure difference. So for your exam, again, it could give you any of these three, okay, and you would have to work out the fourth one, okay? So make sure you're comfortable with rearranging this equation. Another important concept you need to be aware of is the upthrust of an object underwater is equal to the weight of the water it displaces, okay? So just remember that the upthrust, which is obviously the upward force that the water can exert on any object that is on the water, is equal to the weight of that water that gets displaced by that particular object. So, when an object is placed in water, the pressure of the water exerts a force on it from every direction. The pressure on the bottom of the object is different to the pressure on the top of the object. This causes a resultant force upwards called upthrust. Okay, so what upthrust is it's essentially due to the pressure difference. So if we look at this block here, okay, so we know that there's going to be greater pressure on the bottom surface here as opposed to the top surface, okay, because the liquid is more dense compared to the air, which means we're going to get an overall upward force, or we're going to get an overall resultant force. Okay, now here Z has got liquid on the top, so, and obviously it's clearly more dense than X and Y, which means that the pressure difference isn't going to be as great as X and Y either. Okay, so the reason why Z here does not float is because there's no resultant force moving upwards. That's because the pressure on the top surface and the lower surface, the difference isn't as great, and that upward force is less than the weight of Z. Okay, so Z is clearly more dense than X and Y. Okay. So it says the diagram shows 3 blocks in water. The blocks are all the same size and shape, but are made from different materials, which obviously means different densities. Compare the upthrust of the cubes. Well, Z has the biggest and Y is the smallest. Okay, you may be thinking, hang on a minute, how on earth is Z on the bottom and Y is on the top if Z's got a larger upward upthrust force? Well, remember Archimedes stated that the weight of the water displaced is equal to the upthrust. Okay, it's the weight of the water displaced. Okay, so it's the amount of fluid that Y sends out of the beaker, or Z sends out of the beaker individually. Okay, but the weight of the actual blocks might be different to the weight of the water displaced. So Y, in actual fact, is actually lighter than Z, which means although the upthrust on Z is greater than the upthrust on Y, Y's got a lower downward force, which is the weight of the Y, whereas Z has got a greater downwards force, which is the weight of Z. Okay, so that is the reason why Z obviously sinks and Y floats. Okay, let's look at this final exam question. So the blocks in the diagram are cubes with sides of length 20 centimeters. Okay, so they've all got a length of 20 centimeters each side. The area of each side is 400 centimeters cubed, and the volume of each cube is 8,000 centimeters cubed, okay, which is that equivalent in meters cubed. The density of the water is 1,000 kilograms per meters cubed. The bottom of block Y is 10 centimeters below the surface of the water. Okay, so we know that this distance here, that vertical height, is 10 centimeters, and that's going to be important in this equation. Okay, so we want to work out first of all the pressure of the water on the bottom of block Y. Okay, so here we go. The equation is pressure is equal to that vertical height, which we're going to use as 0.1 meters, because that's 10 centimeters, times the density of water. Yes, we've got SI units, 1,000 kilograms per meters cubed, so times 1,000 times gravitational field strength, which is 10. That will give us 1,000 pascals. Okay, so that's the pressure at the bottom of block Y. Now let's use the pressure and the area of the bottom of the block to calculate the upthrust on block Y. So here we go. So force is equal, because remember pressure is force divided by area, which means if we rearrange the equation we get force is equal to pressure times area. Okay, so that pressure that we just worked out, 1000 pascals multiplied by, because the area of each side, it tells us in the question, 400 centimeters cubed, which is 0.04 meters cubed. So that's 1000 times 0.04, that gives us 40 newtons. Okay, so that is the force, that's the upthrust on block Y. Then the weight of block X is 64 newtons. Okay, what is the upthrust on the block? Explain your answer. Okay, so that tells us that the weight of block X is 64 newtons. And we know block X is floating, okay, so it's not accelerating, so its motion is stationary in the vertical plane, which means that the weight of the upthrust has to also equal 64 newtons, okay? So it's a simple principle, forces are balanced, and if it tells us the weight is 64 newtons, it means we've got to have the same upward force, so it's also 64 newtons, so that's why it is 64 newtons, okay? The forces are balanced because the object does not accelerate, okay? It's literally floating, it's not moving. So the upthrust is caused by the pressure acting on the bottom of the block. Calculate the pressure. So we know pressure is equal to force over area, so we're going to use 64 newtons as the upthrust divided by our area, which it tells us is 0.04 meters cubed of one of the sides. That gives us 1600 pascals. And then finally it says calculate the depth of the water needed to produce the pressure you calculated. Okay, so we're going to use this equation here. We're going to rearrange for h, which is the height. Okay, so we know pressure is 1600. Okay, we know the density, it's 1000 kilograms per meters cubed, as it states in the question. We know gravitational field strength is 10, so 1600 divided by 1000 times 10 is 0.16 meters, which is 16 centimeters. Okay, finally I just want to talk about the equations that you need to remember for your exam. So this is if you're doing both the GCSE 9-to-1 combined science course or the just the triple science physics course. Okay, so these are the equations you need to remember. Okay, so distance travelled is equal to the average speed times time, or average speed equals distance divided by time. That's how I like to remember it. Okay, so if you think about the motorway, miles per hour, that's speed, okay? Miles is a distance, time, hour is time, okay? You should also know acceleration is equal to the change in velocity over the time taken, okay? You can write it in this form here. You get a mark for recalling this equation or and any of these equations that is specific to the question that you're answering as well, so it's important that you remember these. Force equals mass times acceleration, okay? F equals m times a. Weight, which is a force, mass times the gravitational field strength, okay, you can write it like this. Efficiency is equal to the useful energy outputted by the device over the total input energy transferred to that device. Okay, if you're doing the higher tier paper, momentum is equal to mass times velocity. Wave speed is equal to frequency times wavelength. Wave speed is equal to distance divided by time. Okay, density is equal to mass divided by volume. Work done is equal to the force distance moved in the direction of the force. Gravitational potential energy, or change in gravitational potential energy, is equal to the mass times the gravitational field strength times the change in the vertical height. Okay, kinetic energy is equal to the half times mass times speed squared. Power is equal to work done divided by time taken. Okay, there you go. Energy transferred is equal to the charge moved times the potential difference. Okay, charge is equal to current times time. Potential difference or voltage is equal to current times resistance. Power equals energy transferred divided by time taken. Okay, electrical power is equal to current times potential difference. Electrical power is also equal to the current squared times the resistance. And then finally, a force is equal to the spring constant times the extension. So that's if you're doing combined science or the triple science. Additionally, if you're just doing triple science as well, These are the other equations that you need to remember, and that is the moment of a force, which is equal to the force times the distance normal to the direction of that force, and then the pressure equation, which is a force normal to the surface divided by the area of that surface. So guys, that's the end of this video. I hope you find these video lessons useful. Please make sure you remember all these equations, okay? Be creative in how you remember these equations, okay? Create statements or sentences to help you remember these equations, and I wish you well in your exams.